Okay, so let's look at a bit of hash cracking. So the focus of this presentation is really on the ways that Hashcat can be used to crack passwords. What we really want to understand is how secure our passwords are, and to be able to create hashing methods which are highly optimized to be able to protect them. So initially we'll look at some of the types and methods that we have, and then how we use salt within our side of hashing methods, and then on to using LM and NTLM hashes that are used in Windows. And from there we'll look at how we can identify the benchmarks for our hashing methods, and then on to some hashcat analysis. We'll look at then bcrypt, script and pbkdf2, and finally we'll do a little bit of analysis on some standard password dumps. Okay, so we'll just go over some basic theory. So this is a hashing method. Normally takes some data. It could be many bytes of data, or it could be a single byte, or it could be a whole network of data, and then creates a digital thumbprint from it. So our hashing methods are typically a fixed sized fingerprint that we get. So for MD5 it's 128 bits, which gives us 32 hex characters. We can represent it in hex or in base 64, but we can see here we just need to change one letter of input data, and it will completely change the hash signature. An proof method is SHA-1, which is a 160-bit signature, so we get many more signatures in there, and then this produces a longer hash signature for us. There are less chance of having what's called a collision with inside our hashing method, the bigger the signature we actually use. Okay, so we can see here we change one letter and some text, and it completely changes the hash signature. And we also see it with inside our Windows systems. So at one time the hashing method of MD4 was used to create what's called an NT hash. So in that way our password would get converted into this MD4 hash or NT hash. We see it also in routing devices, such as for the Cisco config here. You can see here we're using an MD5 encoded hash for our password. As we'll find, it's not really a very secure method. The one way to crack passwords, hashed passwords, is by a dictionary attack. So with a dictionary attack we build up and we keep trying different passwords until we find a match. The other method that we've got is a rainbow table, and with the rainbow table we pre-prepare a whole lot of hashing methods, and then all that needs to happen is that we compare the hash with the values in the rainbow table, and then we can reverse back into the original data. So let's look at the basic methods that we have for hashing. So we've seen SHA-1 and MD5. SHA-3 is a new method that should be highly optimized for IoT devices and uses a new hashing method which should be fairly secure for the future. RIP-EMD is used actually in Bitcoin addresses, produces a 160-bit hash. Tiger, 192-bit hash. bcrypt we'll see a bit later on, and LM hash is used with inside our Windows systems. They don't all have to be cryptography functions. We can get extremely fast ones that aren't crypto functions and that are based on very simple operations such as shift operations and exclusive ORs. So we have Murmur and FMV, which are two very fast hashing methods that are typically used in something, or could be used in IoT, limited IoT devices. So here's an example here of how hashing is used. So this is in TrueCrypt, and what it is that a hashing method, in this case PBKDF2, is used to generate the encryption key. So a password and some salt goes in. This is quite a slow method that then produces a key. That encryption key is then used to open up a header on the disk, and it will reveal the master key which has been used to encrypt the disk and the different types of encryption along with the hashing method. So here we see that the hashing method is used to create an encryption key. So the problem that we have with hashing methods is that once we've found what the hash is of a value, we can easily reverse it back. So salt is used to increase the number of signatures that we can produce from the same piece of text. So with this, we add a salt value to the hash, such as adding it as a string to the input password and then creating the hash of it. This will increase the number of possible values, and it will make it more difficult to actually find the hash value, because an intruder may have to recompute all the values to produce hash signatures for only one given salt. So here's an example of how the salt is stored. So the value here between the dollars is the method, so that's MD5. And then between the next dollars, we get the salt value. In this case, the salt value is just Fred. And then we get the hashed value, the password's hash value here with the salt. Okay, so when the user logs in, the system will take their password, it will take the salt, and it will recompute the hash with the salt and see if they get the same value. In this case, it does. When we use OpenSSL, we get the same value here as what's in here, so the user has used the correct password. Okay, so here's an example here of OpenSSL. -1 is the method, here's the salt, and we see here in the shadow file, the salt is contained between the dollars here, and then that is used to compute, in this case with Red Hat as a password, the hash, and we should get the same password. In Windows systems, we often use LM and NT hashes. So each Windows machine is identified with an SID that defines the domain ID here. And then we have a sub-authority. So this is a unique ID for the host. Then at the end, we get the user ID. 500 is admin, 1000 is the first user, and so on. The passwords themselves are stored in an area called a hive in the registry, and they are stored on the system file within the Windows System 32 config folder. So here we see the SAM database that stores the usernames and passwords. On a domain infrastructure, the passwords will not be stored on the machines, but will be stored by a domain controller. Okay, so here is the place that the files are actually stored. So it's possible to boot a machine into a single user mode, and then to be able to copy these files off or to create a copy of them. So we can see here there's the SAM there, and we can use a number of tools to be able to dump this file into a format that we can analyze. BK Hive will export part of the system hive, and SAM dump 2. The format that it gives is something like this. So the format that we have is the user, and the user, their ID, LM hash, NTLM hash, some comments in their home directory. Okay, so there's the user, there is their ID, that's admin, there is the LM hash, and then there is the NT LM hash. Okay, so we can then use John the Ripper to be able to crack the hashes, and we can see here he's managed to do it fairly quickly. Another tool that we can use is off-crack. So with off-crack, we load up a rainbow table with inside off-crack, and then that and then off-crack will then go and find the required hash and reverse that into the password. So there are machines that are highly optimized to be able to crack hashes, and often these days they're used as Bitcoin miners. So this one here has 25 GPUs within there, and it can crack 8-character NTLM passwords within 5.5 hours and 14-character LM hashes within 6 minutes. It does about 350 billion hashes per second. This one here costs less than $3,000 and what does 1.5 tera hashes per second. Tera is times 10 to the 12. So let's have a look at some benchmarks for hashing methods. So we start here at the fastest, and then we go here to the slowest. We can see that bcrypt, APR1, Cisco, PIX, PBKDFS2 are very slow methods, while SHA-1 and SHA-256 are very fast. Okay, so here's a few examples of what the format of the file actually looks like. You see some of them, like this one here has the method, the salt value, and then the hash here, where others are just a pure hash value there. Okay, so what we can do is we can put in some text, and then we should be able to get a benchmark for it. Okay, so if you're interested, here's the Python code to implement this, and in some of the cases what we feed in is a salt value. In this case for descrypt, we feed in a salt value, and in this case there's the salt that we're actually using. Okay, so we can see that these methods are very fast, whereas the other methods, as I said, like bcrypt, are very slow. So typically GPUs are used to be able to crack hashes because they have many cores, and the CUDA architecture is highly optimized for cracking hashes. So in this case we can see that there are 4 processing clusters on here, and the number of cores that we have, the number of CUDA cores in this case is 3,584. So that will allow us to create a parallel system where each of the cores can actually compute our hashes. One problem with this type of system is that it requires often a great deal of power. And we can see this with Bitcoin mining, where whole factories are set aside to be able to crack hashes, or to be able to create the hash of the current block on blockchain. So this shows you some benchmarks here. So we're using Hashcar to benchmark -b option for the number of words that can be benchmarked. So in this case we're using an i7 processor, and we can see we get 11.2 million words per second. But if we look down here, we're using 2 GPUs, a fast one and a slightly slower one, and we can see here that now the rate is 13,900 22 mega hashes. Okay, so we've went from 11 to 14,000. So it's at least 1,000 times faster with our GPU as opposed to a standalone CPU. And we see devices used for mining. In this case, it's Ethereum mining, where it's highly optimized to be able to crack Bitcoin hashes or find Bitcoin hashes. So now let's look at Hashcat and what Hashcat can do. So Hashcat has three main attack vectors: a rule-based one, where we can set up rules such as take the word password and make the case of the letters uppercase, or add a 1 onto the end. A dictionary attack, where it will go through a standard dictionary of well-known passwords, and then eventually the slowest method of all, but probably the most successful, is a brute force attack, where it searches through a standard. It will go through all of the permutations of character sets. So the main attack modes are brute force, a combinator. Combinator will take words and add them onto each other. Dictionary will take a standard dictionary of passwords. Masking methods, where we can actually define an outline mask. Rule-based, where we define the rules for building the passwords. Toggle-based and hybrid. So hybrid will allow us to be able to mix several methods, and toggle-based allows us to toggle maybe the last character or the middle character, or change an A to an at, and so on. So here are the main options for Hashcat. So the -m will give us the hashing type. Okay, so this value here defines the hashing type. We then define the hash file that we're going to use, and then after that either a mask, word files, or directories. Okay, so this is a standard syntax that we might use. As we showed earlier, -b gives you a basic benchmark for the amount of hashes per second. R gives us the rule files, -o gives us an output file, and so on. So the attack mode that we can use, as we saw, are these ones here. So a combination attack allows us to combine words together. Brute force will go through combinations of letters, and so on. Okay, so the method, the hashing method, is the -m. So we should know the type of hash that we have. So 0 is MD5, SHA-256 is 1400, script is 8900, and so on. And there are different hashing techniques that we can use here. So we define the -m and then the value that we have for the hash type. We can then output in different formats so that we can actually process in different ways, and that's with the -o. Okay, so this is how we use Hashcat here. So what we'll do is we'll have a quick look. Okay, so we'll try an NTLM hash. Okay, so it's our 1000 that we're using. We'll try that there. And we can see here that the hash of help is that. Okay, so this is what the hash for NTLM looks like. Okay, so we can also do a combinational attack. So that's where we have two dictionaries, and then what we can do is we can bring the dictionaries together to be able to create our target. So in this case, we're using one dictionary here and another one, and you can see we go through the first dictionary and then find the first word and then combine it. So for this we use the minus A1 option. So for brute force we'll use a series of, or a combination of characters. So we need to understand how many we've got, and so for a 7-digit A to Z lowercase, how many passwords can we get? Well, it will be 26 to the power of 7 will be our total number of passwords. For this, for lowercase and uppercase, it will be 52 to the power of 7, and then for this it will be, I think, about 60 characters there, 60 to the power of 7. So what we can do is we can then use our calculator to be able to work that out. So 26 to the power of 7 gives us that number of passwords. Then if we want to find out how long it's going to take, if it takes 100 billion cracks, then it'll take 0.08 seconds to be able to crack all of the passwords. Okay, so that gives you an idea about how powerful a cracker can be, and how it relates to the number of characters in the password. So with brute force we can use a number of character sets. So the question mark L gives us our lowercase, U gives us uppercase, and so on. And we can use a custom character set if we want. Okay, so with a custom we can actually define our own, and then we can put in extra characters such as the question mark D, which will add in a digit at the end. So for this case it will use those characters and then add a number at the end. Okay, so let's try an example here. Okay, so we have an LM hash, and then what we're going to try to do is use brute force to be able to crack that. Okay, so we'll just see what our commands are. So the command we're using is the -3. So we're going to use that one. So we're going to use a letter. So we'll just copy that and we'll paste. Okay, so it didn't take too long there. So you can see it's tried 1 character, then 2 lowercase characters, 3, and then 4, and it's eventually found it. So it didn't take long for a 4-character password to crack it by brute force. Okay, so it's going to try from all A's up to all Z's, up to the number of characters that we've actually defined there. One thing we should see is that it will actually tell us how many different passwords it tried for each mask. 26, 676, which will be AA to big Z's, and this will be AAAA to ZZZZ, and then here it'll go from that's the total space AAAA up to ZZZZ, and it found it about halfway through the space. And then for this one, what we can do is that we can actually start with HAL, and then we can actually add 1 letter. If we know that it's going to be if it's going to be made up of these letters, we can more efficiently move through. So you see it's only doing one search, and then it will go through of the 26 possible characters at the end. It found a character 16, which is obviously a P. So we'll just try that out. Okay, so there it's there. It's found help. We can see here it only tried the H, the E, and the L there. That was only one attempt, so it hasn't went through the permutations. And then for this one, it's went through 26 different characters, and it found it at character 16. It went through 61%, over 61% of the space that we've actually specified. Okay, so that's our example there. With brute force, we can also define with a number at the end. Or a digit. So let's see if we've got that. Okay, so it won't be able to find it this time, but we should be able to see our values there. So we can see tried 10 of 10, it didn't get there. So now if we just try our so if we wanted, we could actually create another hash. Let's try one with a digit at the end. Okay, and what we want is an NT LMNT hash. So this is one here. Okay, so let's try that again. And we can see it's found it. Okay, so it's found it there, and it was because it searched through the space of numbers. Okay, we can also do rules and lists within Hashcar. So with this, we can use the standard list like the RockU format, which are the passwords that were generated from the RockU hack. Okay, so it's stored in this place here. And then what we'll do is we'll just list one page. And you can see here, these are the common passwords that many people use. Okay, and there they are. There are over 14 million passwords in there, so it's a fairly large amount of passwords. So we can try for our own one. So in this case, I've created a file which has an MD5 signature in it, and let's see if we can crack it from the RockU password database. So there we go, it's found it, and the password is 123456789. So it has this number of passwords that it is going to try, and it caught it at the fourth password. Okay, we can also define certain rules to be able to modify our passwords. We can make something, we can take a password and make something lowercase. We can make it uppercase. In this case, we'll change the P there into an uppercase. Typically it'd be for the first letter. We can capitalize just the first letter if we need to. We can append a number or something on the end of something, and we can prepend something at the start. And we can also replace parts of it too. There's a number of pre-prepared rules that we can actually use with inside Hashcat if required. Okay, so here's an example here. We can make it lowercase, uppercase. We can capitalize with a C, add a 1 onto it, add a 2 onto it, add a 3, add 1, 2, 3 at the end, and substitute. In this case, substitute an A for an ampersand. So typical things that users will do is to capitalize the first letter, add a 1 or a 2 or a 0 at the end, add 1, 2, 3, substitute an A for an at sign, an L for a 1, 5 for an S, 3 for an E, and a 0 for an O, or an O for a 0. So we could take Edinburgh and we could capitalize the first, we could take the I, make it into a 1, and add 1, 2, 3 at the end. Okay, so in this way we can actually define a rule set to be able to run and to modify the passwords that we have. We can also use the battlefield hash to train against. So this was taken from a real hack, and we can try to be able that against the RockU set. Okay, so in this case, we've got the battlefield. So I've downloaded the battlefield hash. Here they are, in MD5 glory. And what we can do is we can try the same one again, but this time we'll try it with the bfield.hash. And let's see how quick this is. Okay, there you go. We'll just Control C, and you can see how easy it was to be able to crack those hashed MD5 values, because they're not salted, so they're actually quite easy to crack. So 3 methods that are extremely good at protecting hash passwords are bcrypt, pbk, dfs2, and script. Okay, so for bcrypt, what we have is 2a for our method to define that it's bcrypt. We then have the number of rounds that it goes through. So it hashes, and then it goes around again, and it will hash again. In this case, it will hash 6 rounds. Each time it doubles the hash time. So if we went to 7, we'd double it again. If it took half a second, then it's going to take a second. And up to 31 will actually take a long time. It then has a long salt value that is used, and a long hash from them. To give you some idea of the benchmarks, we can see here that for this instance on the EC2 cloud, we do 25,000 hashes as opposed to 38 million hashes with MD5. So here is an example here. Okay, so that's hello. We'll add some salt. Oops. Okay, so there's the hash. This is the salt that's been added, and the number of rounds. So we've only went for 6 rounds. If we took more than that, then it would take a long time. So if you're interested, here's the Python code which I've used to be able to create this hash. But with 20 rounds, then it will take a long time to compute the hash. A script is an interesting one because it will create a hash with salt. There's a block size, and then there's a CPU memory cost, which will increase the computation by a power of 2 each time. And then finally there's PBKDFS2, and for this again we hash for a number of rounds, and this is used inside WPA to be able to create the hashing function to make it difficult to crack the hash. Okay, so we'll go for 7 rounds here. That's it created. There's different PBKDFS2 formats, but if we increased it, then it'll take a lot longer to be able to compute the values. Okay, so these 3 values, these 3 methods are actually very useful in terms of creating a slow hash method to make it more difficult for an intruder to crack. So finally, here's an analysis that we did on 2 of the hacked databases, 163com.txt and rockq.txt. You can see here the top password length was 8 characters, and nearly 1 in 4 actually were only 8 characters long. In the rockq, again, it was 8 characters, and that was 1 in 5 of the passwords were only 8. Quite a few had 6 characters here, 17% and 13%. And then when we looked at the masks, 7% of the masks had a number of letters followed by 2 digits. That was the top value here. I can see these ones here also had similar types of masks. And then in this set here, 58% of them had some sort of numeric character set contained in them. 30% had lowercase letters completely. For some of the advanced masks, the top mask was this one here, which has a number of digits, and that's obviously relating to something like 1, 2, 3, 4, 5, 6 and sequences of digits. Okay, so that's been an analysis of hash cracking, especially looking at Hashcat and some of the more difficult hashing methods. Okay, thanks.